Hello everyone, welcome to this lecture video tutorial in Calculus 3. Enjoy learning. Hello everyone, this is part 3 of lesson number 5 and we will be discussing limit comparison test. This is the last part. Okay, so anyway, this test is it requires that, as you can see here, it requires that your sequence an and bn are two positive term series. Okay, this means that our a sub n, the terms, and b sub n are positive for all n. So the first theorem says that uh, if the quotient, so it doesn't say if an is greater or smaller than bn. Okay, so all you have to do is to know that the given series are positive term series. Okay, so first is get the quotient, and after getting the quotient, take the limit as n approaches to positive infinity. If the answer is a constant c which is greater than 0, then the series both converge or both diverge, meaning to say, if the series is this is your given series. Okay, if, for example, if your en is your given series, and then b sub n is the test series. Okay, if your bn is convergent, then if it satisfies this condition, then the original series is convergent. But if the series is divergent, your bn is divergent, then if it satisfies this condition here, then the original series is divergent. Okay, so if divergent, if en is if bn is convergent, then en becomes convergent. If bn is divergent, then en is divergent also. Okay, so for the second theorem and the limit comparison test, if your quotient as you take the limit is 0 and your bn, okay, this is the this series that that you are going to find, then if this series is convergent and the limit is 0, then the original series a sub n is convergent. Okay, and then if the series is if the quotient is, this one is of an and bn, as you take the limit is positive infinity and your bn is divergent, then en is also a divergent series. Okay, so this is how you are going to use the limit comparison test. So let's have an example to make it more understandable. So let's have example number 1 here. Example number 1. So here we are going to use example 1. Use the limit comparison test. Okay, LCT. Before we will try to answer the to give the first example, let me give you a a note here that the what they call this one, that the limit comparison test, okay, is very much handy if your original series or the given series that the series that you're going to find is a rational function. Okay, So let me put a note here. Note, uh, the limit comparison test is very much handy if uh, the given series uh, the given series the given series in which a sub n is a rational function, is a rational function function n. Okay, so let's have an example here. This series summation summation of n squared over 4n cubed plus 1. Your index starts from 1 up to positive infinity. Okay, let's try. So before, let's wait for the program to respond. As you can see here, clearly our a sub n is a rational function of n. Okay, so this is a rational function of n. So it says here in the note, okay, that it says here in the note that LCT is uh, very easy to use in this kind of situation. Okay, so let's move up. Can we use another color, like say green? Let's put a barrier here. Okay, can we happen? What happened? Do we have an internet connection? Yes, we have. So what happened? I guess it's hanging up. Okay, anyway, what happened here? Okay, so let's put a put a barrier here. Okay, let's have a solution. How are we going to solve this? Okay, in determining the convergence, this is a note. Okay, this is a note. We have to put a note again. Okay, what happened? Let's wait again. We have an internet connection. So this is the problem if you have a very low spec specs laptop. uh, Note. This is a note again. Okay. In determining the convergence or divergence um, of the series, please remember that only that, can we use another color here? Maybe that only the tails matters or matter. Okay, what does this mean? When you say tails matter, this says that the numbers that you are going to consider are those numbers that are very, very, very large. So notice that our n here start from 1 up to positive infinity. So when you say only the tails matters, it says that those numbers that are big enough, large enough, like your n is 10 million or 10 billion or 10 quadrillion, so those numbers are only matters. Okay, so what does this imply? So meaning to say, when when the uh, when the n is large enough, okay, meaning those numbers that are very, very large, the highest powers highest powers uh, in the numerator and denominator uh, matter the most, matter the most. Okay, so please remember all these things. So this means that, let's move upward. Okay, can we put the division here and put the division here? Okay, so this means that uh, a sub n, our a sub n, which is uh, what is our a sub n? Our a sub n is n squared over 4n cubed plus 1. Okay, behaves like so I've said that here the highest powers, as you can see, the highest powers in the numerator and denominator, okay, matter the most. So meaning to say, the constant or other, example in the numerator of this uh, term, okay, sub n, the n term, notice that the highest power, if there are other terms here like plus 3n plus minus 4, you have to eliminate those. Okay, and in this one, if there are other powers of n like 4n cube, 4n squared, other than that, you have to eliminate. Okay, so that's basically what this means. The highest powers in the numerator and denominator matters the most. Okay, so this means that en behaves like this one. So you have to okay, that one. Okay, n cube, no, the n cube we have n cube. So you have to eliminate all the lowest powers, consider only the highest powers, then simplify. You will have 1 over 4n. Okay, 1 over 4n, and our bn here is basically 1 over 4n. Okay, but you can use bn to be 1 over n. Okay, the simplified one. Okay, which is does not include the what we call this one, the constant 1/4. Okay, so but it's okay if you use 1 over 4n, the same result. Okay, so that's our bn. So therefore let's move upward. So there's many mosquitoes here. Do I have an internet connection? Yes. So thus from here the limit, let's multiply here and also here. What happened? Thus the limit of a sub n over b sub n as n approaches to positive infinity. So substitute your an is n squared. Okay, sorry. Again, let's wait for the program to respond. Let's wait. What happened? This is an. Can I erase this? Okay, so maybe that's okay. N squared over 4n cubed plus 1. Okay, RBN, so it depends which one will you use. Okay, but if you use, let's say, the original 1 over 4n, that's okay. But let's try to simplify that later if you use 1 over n, if we have the same result. Okay, this is 1 over 4n as n approaches to positive infinity. Okay, so simplify. We have n squared over 4n cubed plus 1 times 4n over 1 as n, okay, as n approaches to positive infinity. Okay, let's move upward. So from here we have the limit of, so combine the numerator, we have 4n cubed over 4n cubed plus 1 as n approaches to positive infinity. So simplify, we have the same what do you call this one, the same exponent in the numerator and denominator. Then since this is infinity over infinity form, so we can multiply both sides by 1 over n cubed. So and this will become 4. Okay, let's move upward. What happened? Again, we have an internet connection. As n approaches to positive infinity, so this will become 4 plus 1 over n cubed. Okay, am I right? So the limit is 4 over 4 plus 0, or this is equal to 1. Okay, So as you can see, our c, which is this is greater than 0, okay, and we know that the series that we compare is a divergent series, okay, a divergent series which is a harmonic series, okay. So therefore, uh, let's wait again for the program to respond. Okay, so what happened? Let's see here, this one corresponds to a series, okay, corresponds to a series uh, which is divergent, which is a divergent series, okay. Why? Because as you can see, you will have 1 over 4n 1 to positive infinity, and this will become 1/4, 1/4, 1/4 is, that's 4, 1 over n, and it starts from 1 to positive infinity. This is a harmonic series, okay, harmonic series. So this is a divergent series, so therefore, okay, we compare it to a divergent series, okay. Therefore by LCT, the original series is a series which is summation of n squared over 4n cubed plus 1 to positive infinity is divergent, okay. So that's our first problem, okay. For the second, it will be come after this, is that I will give maybe 4 or 5 examples in order for you to visualize if you encounter such kind of problems in your module, okay. So let's wait for the second example. God bless. For our next example, we have number 2, summation of 3n cubed minus 5n over n squared times the quantity n minus 3 times the quantity n squared plus 2, where n starts 4 up to positive infinity. Okay, solution. Notice that in our example, the index start at n is equal to 4. It is because, as you can see in the denominator here, we have the denominator becomes 0 when n is equal to 0. Okay, when n is equal to 1, it's okay. When n is equal to 2, it's okay. But when n is equal to 3, we have 0 again. So meaning to say, if we will start at n is equal to 1 or 2, and we know that when n is equal to 3, the denominator is 0, then we have an undefined. So when n is equal to 1, so for example here, let's have when n is equal to 1, so we have a number here, which is the denominator becomes 3 3 times negative 2 is negative 6, so we have negative 6. Okay, so when n is equal to 0, so we have undefined. When n is equal to 1, okay. When n is equal to 2, okay. When n is equal to 3, we have a 0 denominator. Okay, when n is equal to 4, we have okay. So meaning to say, in these terms, in this term here, we have a problem when n is equal to 3. So this is n is equal to 1, n is equal to 2, okay. N is equal to 3, not okay. So we have x here. Okay, so this is okay. So the problem is this portion of uh, n here, which is n is equal to 3. So we will start our n to be 4. Okay, so anyway, if ever that there is a 0 in the denominator, then the series becomes automatically undefined. Okay, so just like before, in the first example, in determining the convergence or divergence of the series, we know that the only details matters. Mean to say, uh, only those numbers that are big enough or large enough. Okay, so for very large n, only details matters. Meaning to say, the exponent and in the numerator and denominator matter the most. So to answer this problem, for very large n, an, which is equal to this one, 3n cubed minus 5n over n squared times n minus 3 times n squared plus 2, behaves like uh, so the highest exponent in the numerator is this one. Okay, in the denominator, as you can see, we have 3n cubed minus 5n, n times n squared is n cubed times n squared is n to the 5, n times 2 to n times n squared is plus 2n cubed. Okay, negative 3, so negative 3n squared times n squared is negative 3n squared, 3n to the 4. Okay, and negative 3 times 2 is negative 6, so we have negative 6n squared. So the highest exponent is 5, so we have n to the 5. Okay, sorry, no constant, n to the 5. So we have 3 over n squared. Okay, so basically here, you will have our bn. So this implies that our bn is 3 over n squared, or you can drop the 3, 1 over n squared. doesn't matter. Okay, so thus the limit of a sub n, okay, over b sub n as n approaches to infinity. So you can choose which of these two. So but this corresponds to, let's say, okay, let's wait for the program to respond. This one, this corresponds to 1 over n squared, or n starts from 1 to positive infinity, and we know that this is a p-series. This is uh, this is a p-series with p which is equal to 2 and convergent. Okay, so just recall your p-series. So our a sub n, as you can see here, so substitute 3n cubed minus 5n over n to the 5, arrange 3n to the 4 plus 2n cubed minus 6n squared over 1 over n squared as n approaches to positive infinity. Or you can choose this one. It doesn't matter. If this is 3, then you can factor out 3 constant times a convergence series is convergent. Okay, so simplify. You will have limit of, okay, we can use our algebra here, minus 3n to the 4 plus 2n cubed minus 6n squared times this will become n squared over 1, okay, as n approaches to positive infinity. We further simplify. We will have 3n to the 5 minus 5n cubed over n to the 5 minus 3n to the 4 plus 2n cubed minus 6n squared. So are we correct in, okay, we are correct. We have 2n cubed minus plus minus plus minus. Okay. As n approaches to positive infinity, so we have to multiply both sides by this. Just recall your calculus 1 about limits at infinity or infinite limits. I forgot the title. So we have 1 over n to the 5. You can multiply 1 over n to the 5. Okay. Again, let's wait for the program to respond. So simplify. So we have 3 minus 5 over, so 5 over n squared. In the denominator, we have 1 minus 3 over n plus 2 over n squared minus 6 over n cubed as n approaches to positive infinity. So we can now evaluate the limit, which is 3 minus 0 over 1 minus 0 plus 0 minus 0. So this is equal to 3, which is greater than 0. Okay, so what says the uh, limit comparison test theorem? It says that if our t if our c if our c is greater than 0, as you can see here, let's move upward. Let's move upward. Okay, as you can see here, if the limit uh, of the quotient a sub n over b sub n is a constant which is positive, if both are, if the sequence that you compare is convergent, then the given sequence or the original sequence is convergent. But if the series that you compare, which is the b sub n, is divergent, then the original series is also divergent. Okay, so we can use theorem 1, okay, for the limit comparison test. So let me recall, if the for theorem 2, if the quotient, if the limit is 0, then the one that you compare, b sub n, is convergent, then the original series is convergent. If the limit is positive infinity and series that you compare, which is b sub n, is divergent, then the original series is divergent. So for our example, we have theorem 1. So for our conclusion, again, let's wait for the program to respond. So we have an internet connection. So what happened? Let's move down. We're almost there. So we have conclusion. Therefore, by limit comparison test, the original series is convergent. The original series, let's move backward. Can we, again, let's wait for the program to respond. Let's wait. We have an internet connection. The original series summation of 3n cubed minus 5n over n squared times n minus 3 times n squared plus 2, where n starts at n is equal to 4, is convergent. Okay, so that's our second example. Okay, for example number 3, we have this problem: summation of ln of n over n raised to the power of 3 halves, where n starts from 1 to positive infinity. Okay, solution. Sa resolution here. Okay, before we answer this problem using the limit comparison test, notice that in the previous examples, example 1 and 2, notice that a sub n are rational functions of n. So the method there is not applicable in this kind of a problem. Okay, and also notice that in the previous example, since it is a rational function of n, I've said that the only matters are details of the sequence, meaning to say you consider those numbers that are really large or sufficiently large, like your n is 1 billion or 1 trillion. So, and as you have noticed, the only the only matters are those highest exponent in the numerator or in the denominator. Okay, so all you have to do is to eliminate those terms in the numerator which is of lowest exponent, and also in the denominator. Okay, so in here, notice that in this problem our en is ln of n over n cubed. Before we try to solve this problem, let me define this first. Okay, recall, maybe you did not encounter this, but I will put this as a recall. This is the definition of the rate of growth of a function, meaning to say which function goes faster than the other one. Okay, so let's define it first. Okay, we say let's choose another color, say blue. We say f of x grows faster grows faster than g of x. And let's go back to color purple. Again, let's wait for the program to respond. We say f of x grows faster than g of x if the limit of f of x over g of x as x approaches to positive infinity is equal to positive infinity. Okay, meaning to say if the limit of f of x over g of x is positive infinity as x approaches to positive infinity, then f of x grows faster than g of x. Okay, that's what we mean by what they call this, f of x grows faster, or equivalently, or equivalently if the limit of g of x over f of x as x approaches to infinity is equal to 0. Okay, so meaning to say, if the limit of the quotient, this time it's reverse, as you can see here, f of x is in the numerator while g of x is in the denominator. Here our g of x is in the numerator and our f of x is in the denominator. And if the limit is 0, meaning to say that f of x grows faster than g of x. So we write this as this in this symbol. This is not an inequality symbol. Okay, we can also say uh, that let's try this color, that g of x grows more slowly. Okay, so what happened again? Let's wait for the program to respond. Let's wait a little more. So what happened? Can we, okay, so grows more slowly from we say, can also say from f of x. From f of x is, we can also say that g of x grows more slowly from or than, let's say, can I erase this one, than f of x. And we write we can write g of x, this is the symbol. Anyway, they are just the same. Okay, these are a known result or known definition. This is the definition of the rate of growth of if you are given two functions. Okay, let's move up. So these are the established what we call this one, established known results for the rate of growth, for sequences as n approaches to positive infinity. Okay, let's try it. So this is the known result for P and Q satisfies this inequality, and your A and B satisfies also this inequality. We have this one, ln of n n to the p is much faster. Okay, n to the q a to the n, b to the n. No, not this one. I'm sorry. I write it as, sorry, an inequality symbol. So let's wait again. And a to the n. No, this one. B to the n. N factorial. N to the n. So notice here, n to the n is much faster than n factorial. Okay. So with this, established known result, okay, this is the established known result. As you can see, what happened. Let's wait again. What happened for our program? Do we have an internet connection? Okay, I'm sorry. I think I have to delete that one. Okay, let's move up. With this result, for example, this one, since this is true, for example, this one here, ln of n is much is slower than n to the p. Okay, for any constant p which is greater than 0. This means to say that based on the definition, the limit of ln of n over n to the p as n approaches to positive infinity, this is 0. Okay, this is what basically this means. Okay, so to solve our problem, we can say, thus since we know that the remember, please recall that our an is ln of n over n to the 3 halves. Okay, n to the 3 halves. So that happened, ln to the 3 halves. Okay, notice here that since our what I call this one, since our an satisfies this relation, okay, satisfies this relation, meaning to say that the limit of ln over n raised to the power of 3 halves as n approaches infinity is 0, meaning to say that the this means that our denominator is much grows faster than the numerator. This means to say that our ln of n is, this is true. Okay, this is true 3 to the, what I call this one, No, I'm sorry. Can I undo this one? Our denominator satisfies this one. Okay, but this is our what they call this one. Uh, our en satisfies this one. Let's try another color. Let's wait. What happened? Let's wait for our program to respond. That's we have an internet connection. Okay, so meaning to say our en satisfies this one. Okay, satisfies that one. Meaning to say for any constant p which is greater than 0, our function n to the p is much faster than ln. Okay, so from here we can choose our p to be not 3 halves, but we can choose any other constant which is greater than 0. However, there must be a what we call this one, a right way on how to choose the constant p. Okay, so this p here that I will choose is 1/4. Okay, or shall I say, let's say 1/4. Okay, we will choose our p to be this one, 1/4. Why? This inequality, somehow you will notice that this is not true for small values of n, like when n is equal to 2, 3, 4, 5. Notice that this is true for let's say for sufficiently large n. So what do we mean by for sufficiently large n? Okay, but anyway, you can choose your p here to be 1/4. Any between, when I studied this one, you can choose your p to be between what do you call this one, to be between, your p must be between this value. Okay, you can choose that for any value p here, but if it is greater than 1/2, then there's a problem. I will show to you later why. If you choose p to be greater than or equal to 1/2, then although the inequality is true, then the LCT will not cannot satisfy the LCT, the limit comparison test. Okay, so remember that one. There's a right way on how to choose this, so all you have to do is to make yourself what they call this one, make yourself study more, or make it more play just play for any values of p. Okay, and then you will see it later. Okay, if you encounter this kind of problem. Okay, but anyway, so let's try to look at the graph of this function ln and n to the 1/4. Let's try to graph it in Desmos calculator. can see here, for example, we have ln of x. So this is our ln of x, and then try x to the 1/4, x to the 1/4. Okay, enter. So as you can see in the graph, you will notice here that the function ln of x or ln of n, okay, is much greater. It is much greater than x to the 1/4. Look at the values. So example, we have n is equal to 8. ln 8 is much bigger than 8 to the 1/4. Okay, however, as I write here in this one, I write here that for sufficiently large n. So what does it mean? So if you choose n to be, like for example, 10,000, 10,000, you can see here, let's try ln of 10,000. Okay, ln of 10,000, sorry, it's 100,000. Okay, this one. Okay, enter. ln of 10,000 is 9.21034. Okay, but what is 10,000? 10,000 to the raised to the power of 1/4. 1 divided by 4. Okay, enter. So as you can see here, when when your n is 10,000, then the value of x to the 1/4 is much bigger than ln of 10,000. Okay, so maybe you are confused with the graph, but if you look at if you zoom in when n is equal to 10,000, then you will notice that this graph here will, this graph, the blue one will move upward. Okay, no, this is not, is this the blue one? Purple one. The purple one move upward. This is much bigger now than the green graph. Okay, so that's basically what we mean by f of x grows faster or grows slower than g of x. Okay, so this is true for sufficiently large n. When n is equal to 1 million, 1 billion, so you can say that this is true. Okay, and further, if you multiply both sides by n to the 3/2. Okay, if you multiply both sides by n to the 3/2, okay, this is true also for sufficiently large n. Okay, so this is positive, or n is 1 up to positive infinity, so you multiply both sides by positive numbers, so this is true. Okay, and then if you simplify this, we have 1 over n to the, no, not 1/4, this is 3/2. Okay, sorry, n to the 3/2, so 1/4 minus 3/2 is 5/4. Okay, sorry, again, 5/4. Let's try to erase this one. This is 2. Okay, so 1 over n to the 5. So this means this is now our b sub n, and we know that this is a p series. Okay, This is a P series. This is a P series with P, which is equal to 5 over 4, and convergent. Okay, this is convergent. So therefore the limit of a sub n over, okay, remember that if we I will recall it back later, that if you wrongly choose your p, which is not in the interval 0 to 1/2, okay, not including 1/2 is not included in 0, then what will happen is that you cannot use the limit comparison theorem. Okay, a sub n over b sub n as n approaches to positive infinity, this will become ln of n over n to the 3/2 over 1 n to the 5/4 as n approaches to positive infinity. So simplify further, over n to the 3/2 times n to the 5/4 over 1 as n approaches to positive infinity. And then you will have the limit of ln of n over n to the 5/4 minus 3/2 is 1/4. Okay, as n approaches to positive infinity. And notice that you can use the L'Hopital's rule here. Ln of as n approaches to infinity, the limit of ln as n approaches to infinity is positive infinity. Ln of n to the 1/4 as n approaches to infinity is positive infinity also. So we have a form, here which is plus infinity over plus infinity. Therefore you can use the L'Hopital's rule. Derivative of the numerator is 1 over n, 1/4 times n to the negative 3/4, n approaches to positive infinity. So by LHR. Okay, so as you can see here, you can simplify it more. This is 1/4 times the limit of 1 over n to the 1/4 as n approaches to positive infinity. So 1 plus negative 3/4 is positive 1/4. And as you have noticed here, the limit of this one is, of course, based on our calculus 1, this is 0. Okay, so this is 0. So negative, this is 1/4 times 0, so this is 0. Okay, so the limit of a sub n over b sub n as n approaches to infinity is 0. So therefore, accordingly, as you can see here, if you look at your notebook, accordingly the original series is convergent. Okay, so why? So again, if you look at your theorem number 2, okay, so you refer to theorem number 2. Let's wait for the program to respond. Coronavirus. Okay, so let's wait again. From here, use theorem LCT number 2. Okay, so let's move upward. Can we move upward? So okay, I will go back to this case here. If your P is greater than 1/2. So let's look at our theorem. Okay, so I need to go to the theorem. Where are you? Let's wait. So we have an internet connection. Positive. So let's wait a little more. Let's wait for the program to respond. You can see here okay, we are almost there. Again, let's wait again for the program to respond. It's raining outside, so I guess what happened here? Why can't I move to the other side? Let's move here. Okay, so look at the, so we are in this case, this one, okay. So if your limit is 0, limit of the quotient an over b7 is 0, and we should choose our b sub n to be convergent. Okay, it must be a convergent series, because if you choose the series which is divergent, then you cannot use this theorem. Okay, so that's why if you choose your p to be greater than 1/2 or equal to 1/2, then you have a b sub n which is a divergent series. Okay, so if even though if you use theorem number 3, this one, you notice that the limit must be positive infinity. If you choose to be your b sub n to be convergent and the limit is positive infinity, then you cannot use this theorem. Okay, so let's go back again to our at the bottom. I'm sorry, I have, can I move downward? Let's move downward. Okay, we are almost done. Okay, this one. So for example, if you choose here Let's try green one here. If you choose your p, for example, which is 1/2, okay, suppose that you choose your p to be 1/2, then as you can see, this inequality is also true. Okay, ln of n is greater than 1/2. Okay, let's again. What happened? We have a internet connection. Okay, this is ln, this is true. Okay, for sufficiently large n. Okay, so if you multiply both sides by n to the 3/2, n to 3/2, then you will have 1 over n to the 1/2. Sorry, n to the 1. Okay, this is n to the 1, or a harmonic series, which is 3/2 minus 1/2 is 1. This is a harmonic series. Okay, harmonic corresponds to a harmonic series, corresponds to a harmonic series with p is equal to 1, which is divergent. Okay, and then if you take the limit of a sub n over b sub n, a sub n, as n approaches to positive infinity, we can simplify, can substitute the value. The limit is also 0. Okay, but you cannot use theorem, the LCT theorem number 2. It is because our b sub n is divergent, and it says there, if you look at above, in our theorem, b sub n must be convergent. Okay, so be careful on how to choose if you encounter this kind of problem. Okay, this is a sub n, not a to the n. So again, let's maybe we can wait for your program to respond. Let's erase that one. A sub n, this is 0. Okay, but we cannot use theorem LCT number 2. Okay, so for p between these values, then you can use the theorem. We can also argue this one using the direct comparison test. Okay, if you choose the series, then you will see that it will not work. But if you use this this b sub n, sorry, not series, b sub n, if you use this b sub n 1 over m to the 5 over 4, then using the direct comparison test, you can see that the series is convergent. Okay, be careful. Okay, so that's problem number, or example number 3. So for example number 4, just wait a little more. So I'm going to find a very interesting situation. If ever you encounter this kind of problem in the exercises or problems in the books. Okay, Okay, for example number 4. Example number 4. Example number 4, we have summation of 5n squared ln of n plus 7 over 4n cubed minus n squared plus 3n minus 2. N starts say 2 to positive infinity. Okay, so again, just like before, for very large n, a sub n, which is 5n squared ln plus 7 over 4n cubed minus n squared plus 3n. Okay, this is not just like problem number 3. Okay, since in our problem number 3 we have one term in the numerator and one term in the denominator. So this example is just like example number 1 and number 2. Okay, behaves like as you have noticed, we will consider only those with highest exponent in the numerator and in the denominator. Okay, so meaning to say, in the numerator, since we have two terms and the highest exponent is n squared, so therefore we have to eliminate the term plus 7. In the denominator, we have to eliminate the smaller one, the degree 2, 1, and the degree 0. Okay, so it will behave like this one. Okay, and then if you simplify this, we have 5 ln of n over 4 times n, which is clearly greater than. Can further simplify this as can choose 1 over n for all n greater than or equal to 2. Okay, so we can choose our b sub n to be this one, or we can choose this as our b sub n. Okay, so it doesn't matter. Okay, and also this corresponds to a harmonic series. Okay, harmonic series, which is divergent. Okay, so therefore the limit of a sub n over b sub n as n approaches to positive infinity, we have substitute. We have 5 n squared ln of n plus 7 over 4 n cubed minus n squared, first that one, plus 3n minus 2 plus 3n minus 2 over 1 as n approaches to positive infinity. Okay, and then simplify. Simplify, you can reciprocal. Okay, and then move to multiplication. Yeah, limit of 5n squared. I'm sorry, what happened? Okay, maybe can we move upward? This is what will happen if you have a very low internet connection, and of course our laptop is not good enough to handle this up. Okay, so I guess I have to wait. How are you, my student? Okay, let's further simplify. We have 5n squared ln of n plus 7 over 4n cubed minus n squared plus 3n minus 2 as n approaches to positive infinity, and you have n over 1. Simplify, we have 5n cubed ln of n plus 7n over 4n cubed minus n squared plus 3n minus 2 as n approaches to positive infinity. So we have the form positive infinity over positive infinity. So therefore you can use the L'Hopital's rule. Okay, you can multiply both sides by 1 over n cubed. Okay, you can multiply both sides by 1 over n cubed. One over n cubed, 1 over n cubed. This will become limit of 5 ln of n plus 7 over n squared over 4 minus 1 over n plus 3 over n squared minus 2 over n cubed as n approaches to positive infinity. Okay, as you can see, we have 0, 0, 0, but this one, okay, we have positive infinity. Positive infinity times a constant is positive infinity plus 0 is positive infinity over 0, 0, 0. So infinity, or a bigger number divided by a smaller number, is also, as you can see, we have positive infinity. Okay, this is positive infinity. Okay, so this example illustrates theorem LCT, theorem number 3. Okay, so accordingly the original series is convergent. No, divergent, sorry, divergent. Okay, I will erase that one by theorem. This is LCT number 3. Okay, we have our b sub n is a divergent series, okay, harmonic series which is divergent. Okay, so therefore, since the limit is positive infinity, the original series is a, what we call this one, divergent. Okay, so that's I guess that's enough. We have four what they call this one, four examples. Okay, four examples, and I exhaust all the um, theorems. Theorem 1, we have an example for theorem 1 LCT, theorem 2 also, and we have theorem 3 also. Okay, so I hope that you now have a what they call this one, an idea, okay, on how to use the limit comparison test. Okay, for this last example, this is very important because you will be tempted to write the conclusion as a divergent series in the end if you are not careful on how to deal this kind of problem. Okay, so we have example number 5. Number 5, we have summation of n to the 4 over n factorial, where n starts from 1 to positive infinity. Okay, solution. As you can see here in this problem, maybe you will choose b sub n to be the series that we are going to what you call it, to test. Okay, use maybe you will be tempted to use b sub n to be 1 over n factorial. Okay, this one, 1 over n, to use maybe you will be tempted to use b sub n as a test series to show using the limit comparison. Maybe you will tempted to use b sub n over 1 as a test series to show using LCT that wait, just wait. Maybe you will be tempted to use b sub n, which is equal to 1 over n factorial, as a test series to show using LCT. That the series, this one, is convergent or not. Okay, now why is that? We know that in our previous example, in the direct comparison test or in comparison test, that this series, summation of b sub n, where n starts from 1 to infinity, this series is convergent, okay, by direct comparison test. Okay, so if we take the limit of a sub n uh, of a sub n over b sub n as n approaches to positive infinity, we have uh, n over 4 over n factorial over 1 over n factorial as n approaches to positive infinity. Okay, so if you simplify this one, we have n to the 4 over n factorial times n factorial over 1 as n approaches to positive infinity. Okay, and we remain this expression, and this is, we know that this is positive infinity. Okay, so based on the based on the limit comparison test, our b sub n is convergent. Okay, but the limit of the quotient is positive infinity. Okay, so therefore we cannot use therefore we cannot use theorem LCT number 3. Okay, because, sorry, can we go back? Because this one, because summation of 1 over n factorial is a convergent series. Okay, so LCT number 3, theorem number 3, cannot be used. Okay, so don't lose hope. Okay, there's a way on how you can use the LCT here. Okay, so remember that in our previous lesson also, we can, if we discard or eliminate the previous terms, finitely many terms, if we eliminate those terms, then the convergence or the divergence of the series is not affected. Okay, please do remember that. Okay, don't lose hope. Okay, don't lose hope. We can still use the limit comparison test. Okay, so how? Okay, now look at the given what do you call this one, given series. Okay, this is 1 to the 4 over 1 factorial plus 2 to the 4 over 2 factorial plus 3 to the 4 over 3 factorial, and so on up to n to the 4 over 4 over n factorial. Sorry. Okay, this is n factorial. Okay, let's wait again. Do we have an internet connection? I guess we have an internet connection. Okay, so just wait. This one, n factorial plus dot dot dot. Okay, Notice that here we can by previous discussion, we can uh, eliminate, okay, eliminate or subtract a finite number of terms, without affecting the behavior uh, of the series. Okay, remember that finite, this one. Okay, as we shall see below. Okay, so as you can see here, we can write wait, what happened again? Let's wait for the program to respond. As we can see here, as you can see here, you can extend this one. After n, you can have n plus 1 over to the 4 over n plus 1 factorial, right? And then you have n plus 2 over n plus 2 factorial plus n plus 3 over n plus 3 raised to the power of 4 plus n plus 4 to the 4 over n plus 4, and so on. Okay, so we can eliminate let's say can eliminate the first 4 terms. This one, first 4 terms, can erase that one, this one, and the other. Okay, we have 3 to the 4 4 to the 4 here, 4 to the 4 over 4 factorial. So we can eliminate this. We can start at 5. Okay, 5 to the 4 over 5 factorial plus 6 to the 4 over 6 factorial, 7 to the 4 over 7 factorial, and so on. It is you can write this as n to the 4 over n factorial plus n plus 1 to the 4 over plus 1 factorial plus, you can write it here, okay, dot. Okay, so this implies that our b sub n, we choose our b sub n to be n plus 4 over to the 4 over n plus 4 factorial. Okay, and no, this is not, this is our a sub n, sorry. And the same time our bn is 1 over n factorial. Okay, this is a sub n, I'm sorry, I have to rewrite that because we rewrite our series. Okay, let's wait again for the program to respond. Mm, 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 mm. So what happened? Let's move back. Use the eraser. Okay, and then we have a sub n. Okay, so here we let a sub n to be this one. Okay, so this implies that the limit of our a sub n, so this series now, which is our new series, which is the behavior of the series, mean to say the convergence of the series is not affected when you discard or you subtract or you eliminate the first few terms. Okay, this if the series is divergent, then the series is divergent, it will not be affected. If the series is convergent, then the series is convergent even if you discard the first few terms. Okay, as n approaches to positive infinity. So as you can see here, this is n plus 4 to the 4 over n plus 4 factorial over 1 over factorial as n approaches to infinity. Sorry for that, we have a motorcycle outside. Okay, so simplify. This will be n plus 4 to the 4 over n plus 4 factorial times factorial over 1 as n approaches to positive infinity. Okay, let's further simplify. This is the numerator is n plus 4 to the 4 times n factorial. The denominator can be expressed as n plus 4 times n plus 3. This is in statistics. If you recall your statistics, this is how you are going to simplify the factorial notation. Okay, so cancel. So as n approaches to positive infinity. So from here we will have, can cancel out 1. So we have n plus 4 to the 3, and then n plus 3 times n plus 2 times n plus 1. Okay, as n approaches to positive infinity. Okay, you can expand the numerator and the denominator using the special product. So we have special product, cube the first term, cube the first term. Okay, and then plus 3u squared v plus 3uv squared, 3u squared v plus v cube. Okay, as n approaches to positive infinity. How about this one? Okay, we have, let's multiply this one. Okay, so we have n squared, the middle term is 5n, the last term is 3n, 3n, 2n is 5n plus 6, and then n plus 1, and this is n 4 and 4. Okay, so we have n cubed plus 12n squared plus 16 times 3. We have the calculator here. 16 times 3, we have 48n plus 4 cubed, 4 raised to the power of 3, we have 64. So let's see, in the denominator we have n squared times n plus n squared plus 5n squared, 5n squared plus 5n, tapos 6n plus 6 as n approaches to positive infinity. Let's simplify. N cubed plus 12n squared plus 48n plus 64. We have n cubed. We have same terms here, plus 6n squared, and then we have 11n plus 6 as n approaches to positive infinity. Okay, so from here we can use we can multiply both sides by 1 over n cubed. Okay, so let's wait again for the program to respond. So we have the limit, I think it is 1. Okay, we have 1 here. So limit of 1 plus 12 over n plus 48 over n squared plus 64 over n cubed. 1 plus 6 over n plus 11 over n squared plus 6 over n cubed as n approaches to positive infinity. So this is 1 plus 0 plus 0 plus 0 over 1 plus 0 plus 0 plus 0, and this is 1, which is greater than 0. Okay, so we have a convergent, our B sub n is convergent series. Okay, the test series. Okay, so therefore the original series is convergent. So accordingly the original series is convergent by theorem LCT number 1. Okay, so that's how you are going to solve that kind of problem. Okay, so please be careful. There are times that when you choose your B sub n, B as in Bravo, B sub n, if you choose your B sub n, then there are times that you cannot use the theorem as long if it will not satisfy the condition of the theorem, you cannot use it. So be careful, do not rashly conclude. Okay, just analyze, use some other tools like Smapple or any other website that can get the convergence or divergence of a series. And then of course you cannot use the website as your as a solution, but you have an idea on how to that the series is convergent or not. Okay, so just use some other apps, known apps like Mathematica, Maple, or any other apps that you can use to verify yourself that the given series is convergent or not. Okay, and then use the theorem. Okay, so once again, you cannot use the app as your as a part of your solution, but you can it is a tool that you can say that the given series is divergent or not. Okay, so for your assignment uh, use LCT or CT. Okay, number 1, summation of sine 1 over n, where n starts from 1 to positive infinity. Okay, number 2, uh, Summation of n factorial over 2n factorial, where n starts from 1 to positive infinity. Number 3, we have summation of 2 to the n over n factorial, where n starts from 1 to positive infinity. Number 4, we have summation of ln of n over n squared plus 2, where n uh, starts from 1 to positive infinity. Number 5, summation of 1 over 3 to the n minus cosine n, where n starts from 1 to positive infinity. Number 6, we have summation of tangent inverse of n over n to the 1.1, where n starts from 1 to positive infinity. And last is the last problem, 1 plus 2 plus 3 up to n, where n starts from 1 to positive infinity. Okay, these are your assignment. uh, the deadline for this assignment is on Thursday. Okay, and I will announce it later if we can have our third short exam maybe on Friday. Okay, so God bless everyone. Don't forget to subscribe to my channel, and by clicking that red button, subscribe button, and the bell button down below. Thank you so much for watching. God bless everyone. Bye bye.